We all know designing software takes a lot of work. It's not often clear what constitutes a good design. The solid design principles are 5 ideas that can help build software that's easy to extend and adapt. I'm Steve Lott, and I've been building Python applications and writing books about Python for almost 20 years. I'd like to share my experiences applying the solid design principles. In this course, I've got a kind of case study that's a little bit of data analysis and a little bit of data science. I think it's fun because it comes from a real world problem I had with the boat I live on. Join me in my LinkedIn Learning course to see more of the solid design principles. I'll show you how to transform a weak design into great code that's easy to live with. I'd like to introduce the solid design principles. There are 5 principles I want to share with you. First, though, I need to share why these ideas are so important. Software is always in a state of flux. It's essential to ask, what could go wrong when someone needs to make a change to our software? The state of flux is like tossing pebbles into water. Each pebble has ripples. Ideally, each change is isolated. It's best if there's a way to confine the ripples to prevent adverse consequences. In an OO programming language like Python, class definitions can be used to confine the ripples of change. A class allows programmers to isolate the various concerns that comprise working software. For example, we can disentangle algorithms and data structures from the operating system details. The solid design principles provide guidance on how to structure our classes in a way that keeps the concerns separate and minimizes the ripples of change. Here's my real-world problem. It's like enterprise business analytics, and it involves a sprinkling of data science. I live on a boat, and this diesel engine is very important. On the other side of the engine, there's a new alternator. It generates electricity to charge the batteries, and it provides a signal for the tachometer at the helm that shows the engine revolutions per minute, the RPMs. Here's another picture of the alternator. What's important is the serpentine belt on the new alternator has smaller wheels than the old alternator had. It turns faster and generates more current, which is nice. However, I can't easily recalibrate the tachometer, and I certainly don't want to buy a new one. So instead, I want to create a model to translate from the RPMs shown on the old tachometer to the actual engine revolutions per minute. In order to do that, I gathered some data. I ran a few experiments using a photo laser tachometer, which has to be used manually down inside the engine room. Do these tach and engine values even correlate? And if they do, is there a simple regression function that will map readings on the tachometer to the actual engine RPMs? What I did was design this correlation class. It has a method, read, to read the sample data from a file, and it has this method R to compute the coefficient of correlation. And this method got to be kind of complex, and worse, this isn't exactly what I need. I have to make some changes to this class. What can go wrong? I created a class to solve my data analytics problem, but I designed this class without following any of the solid design principles. And while the class works, it doesn't really do what I want. Here are some of the problems. Here's the first one. The CSV column names in the file are wrong. My file doesn't have columns named X and Y. They're called tach and engine. If I try to make this change, there are a lot of places where I need to make that column name change. Here's another problem, perhaps not as big. There are a lot of steps in the main function. This correlation class demands a lot of individual steps to compute the correlation between the two columns. Specifically, it seems really unnecessary to expose the X values and Y values methods. especially because in the long run, the column names are wrong. And here's another big problem. There are a lot of computation steps for computing the linear regression parameters shown in this new method that I'd like to add. It turns out that the code for computing the correlation coefficient is almost identical to this code. But it's hard to figure out how to reuse the original overly complex method. So there's a certain amount of copy and paste in here that is difficult to maintain. There are several problems in my original code. It helps to articulate the problems and some of the consequences of those problems. This is an important first step in applying the solid design principles. But if all I do is identify the problems, I'm not really helping because I'm not solving them. It's important to take the second step and propose a solution based on the solid design principles that will fix the problems and prevent additional problems when we have to make further changes. One key point about the solid principles: they're not a style guide or a superficial approach to developing code. These principles may require significant rework to poorly designed code. I want to start with an overview of the solid principles, and after the overview, each of the next 5 chapters will look at how the principles apply in my case study data analysis and modeling problem. I want to summarize the solid design principles before digging into the details of each principle. Here are the overall goals for solid. First, to prevent problems by giving explicit guidance on design problems that we may not always anticipate. Second, to distinguish style from substance. There are fundamental design approaches that will lead to better software. Here are the 5 design principles that form a handy acronym: single responsibility, open-closed, Liskov substitution, interface segregation, and dependency inversion. It's important to note these 5 aren't the only OO design principles. I'll touch on some others. The don't repeat yourself principle urges a coder to avoid copying and pasting duplicate code. I'll also reference the GRASP principles for guidance on allocating responsibilities to classes and modules. This is a collection of brilliant ideas for locating the single responsibility that underlies the solid principles. Test-driven development can also help create solid design. Creating isolated unit tests for a class tends to reinforce the solid design principles. These principles are not a simple recipe for class design. The principles overlap each other in a number of ways. They have different points of view. Some of these principles look closely at coding techniques, where others look at higher-level design considerations. Solid is an aid, not a rigid formula. As part of demonstrating each principle, I'll show several alternative implementations of the same classes. The question of which is right or which is best may come up, but the question is moot. There'll always be alternative designs for a class. Some designs have higher performance, others use less memory. None of the alternatives is trivially best, but some are more solid than others. The solid principles will help a designer articulate why one design is superior to the alternatives. These principles will say nothing about a large number of software engineering issues. Solid doesn't specifically address resource use, performance, security, deployment, support, licensing, or a host of other design considerations. The solid principles are focused on the ripple effects from change and how well software fits the intended use. I'm not going to show the solid principles in mnemonic order, and while the order's poetic, it's not really pragmatic. I'm going to start with the interface segregation principle. Classes should depend on the smallest interface. This seems to be the most helpful way to start designing a good class. This principle helps us to write unit test cases also. After segregating the interfaces, it helps to look at common code. The common code can become a superclass, and the special cases can become subclasses. The Liskov substitution principle suggests that subclasses must be able to replace their parent classes. When a design calls for polymorphic peer classes, this principle can be applied to each one of the peers. A class needs to be open to extension. There should be no reason to modify the code. I find the open-close principle helps to define what features of a class need to be exposed. A good class can be extended, and making code modifications by endlessly tweaking the class can be avoided. The dependency inversion principle is focused on packaging the code. Some languages have tools and frameworks to help implement this, and other principles help design the classes properly, but this principle makes sure that references avoid concrete class names. The principles related to the concept of late binding. Defer making connections among components until the application is running. And finally, the single responsibility principle. This is a kind of summary of the other four principles. After applying the other principles, the resulting class often has only one reason to change. The single in the name can be confusing because it's not clear what level of abstraction should be used, nor how the responsibilities are counted. But the grasp principles will often help define single in a meaningful way. There are 5 core design principles. These principles will help articulate reasons why the initial design for my correlation class was so bad, and they provide concrete guidance on good ways to design classes and modules and Python packages.